Welcome everyone to lesson 2.3 of Precalculus, which is all about exponential functions. So let's get started. So when we talk about exponential functions, they typically take the form of a times b to the x. We're going to transform these, but by default, we'll just put air quotes around that. They take the form of a times b to the x, where a is our initial value. If we're starting with 1, it's 1. If we're starting with 5 million, then it's 5 million, so on and so forth. And b is the repeated multiplication. So remember that this is our relationship to geometric sequences, which is all about repeated multiplication. That b is our growth factor here, is our proportionality, our common ratio, so on and so forth. So when we talk about exponential functions, there's two major branches, we'll say. Things either grow or they decay exponentially. So growth looks like small in the beginning and growing large at the end, constantly getting larger and larger, and the larger it is, the faster it grows. Decay is the opposite. The more of it there is, the faster it goes down, it decreases, but the less there is, the slower it decreases. So you can think of things like money as exponential growth, or radioactive isotopes as exponential decay, so on and so forth. I like to think of growth instead of saying that something is increasing over time. Growth means that the right side of the graph, as x tends towards infinity, the curve itself, the function itself, is going away from its horizontal asymptote. So it's getting further away from the x-axis by default, but if we shift that horizontal asymptote, then it's getting further away from that. Decay means that it's getting closer and closer to it as x is approaching infinity. So we have these ideas here. What differentiates growth and decay analytically? That would be its proportionality, its common ratio, its growth factor, whatever you want to call it. That b. If b is greater than 1, then it's growth. If b is in between 0 and 1, it's decay. B can't be less than 0. It can't be 0 or less than 0, because if it's 0, you have a constant, you have a flat line. And if it is less than 0, it's going to have this alternating pattern of positive and negative, because even powers make negatives positive, and odd powers keeps negatives negative, so on and so forth. So with all that done, let's identify whether these functions here are exponential growth or decay, and then justify why. So if we're just looking at growth versus decay, what we're going to do is we're going to look at that b value. Right here, the b is 0.6. So I would say that 0.6, that is ugly. 0.6, it's also ugly, but it's fine, is in between 0 and 1, so it's exponential decay. And we're going to try to justify with that, so on and so forth. And you can say in the opposite order that this is growth. I'm going to skip the exponential because I don't want to write it all the time. This is growth because 0.7/5, which is 1.2, is greater than 1. So on and so forth. So 1/6, well, 1/6 is less than 1, so 1/6 is less than 1, so it's decay. And 1.3 is greater than 1, so this is growth. It does say justify your answer, so you do want to make sure that you're including it's this because of that, so on and so forth. I got a little lazy around the end. I'd recommend either what I did in the very beginning or the second one compared to the last two, mainly to make sure that you're getting all the points that you should. So what if we're given some string of numbers being multiplied? Can we create an exponential function based off of that string of multiplication? And can we figure out where that function was evaluated at? So what we're going to look for is we're going to look for the lone number, because the lone number would be our initial value. That would be our a, because remember we're looking at f. Whoop. Let's undo that. We are looking for functions in the form of f of x equals a times b to the x. So the a would be our initial value, would be the one lone number, and the b is what's being repeatedly multiplied. So in the first case here, our initial value would have to be the 1.5, and the repeated multiplication comes from that 4 to the power of x. So this is our first function. And where it's being evaluated at is at an x of 3. Let's write that a little better. X equals 3. So that's happening at x equals 3. That's the function, so on and so forth. We get the general idea. For the second one, our initial value is 3.2. We are repeatedly multiplying 0.8. So f of x equals 3.2 times 0.8 to the power of x would be our function, and we are evaluating this at x equals 2. Not too bad. So we're in pre-calculus, so what we really care about is behavior. We really analyze the behavior of these functions, and we're trying to make determinations and solve problems using this behavior. So let's talk about the 4 major behavior types of exponential functions. So exponential functions, regardless of their form, don't have any maxes or mins. There are no relative extrema here. All of them have a horizontal asymptote. It's either on the left or the right side. It's not both, like it would be with a rational function. It is either always increasing or always decreasing, one or the other, not both. And it's always going to either be concave up or concave down. So it's always going to have those properties. So I've given these names based off of the experience I've had teaching pre-calculus in the past, and these are the names that I used before. And I quite like them because they describe the behaviors quite well, especially with the definitions we set up in the beginning. So positive growth means that the a value is positive. We're above the horizontal asymptote. Growth meaning as we get larger x's, the y's are getting larger and larger, getting further away from the horizontal asymptote. Its end behavior would be described by these 2 limits here. So the limit as x approaches negative infinity, f of x is getting closer to 0. And the limit as x approaches infinity for f of x would be equal to infinity. Positive decay is the decay we talked about before. So a is greater than 0. Our b is in between 0 and 1, which means we're concave up and decreasing. As x approaches negative infinity, f of x is approaching infinity. As x is approaching infinity, f of x is approaching 0. So we can see what's happening there in that behavior. If you want to know why, those are great questions to ask yourself and then ask each other and then ask me in class. Negative growth and negative decay are the reciprocals. We're flipping them essentially. So when the a is less than 0, it's okay for a to be less than 0. It just means that the function itself is going to exist entirely below its horizontal asymptote instead of entirely above. So we get the same kind of idea, though. They're reflections. So negative growth looks like positive growth, just reflected. As we go to the right, the function is moving away from its horizontal asymptote. And decay, opposite, as x is going to the right, it is going towards its horizontal asymptote. That is that. So those are the 4 behavior types, and those are what I call them. I don't know if they're known colloquially or commonly as that, but for me in my class, this is perfectly fine to describe them this way. Let's use what we know now about these behaviors to analyze some functions. So one of my students pointed out that I did this part of the video wrong, so we're going to do it from scratch. So when we answer questions about whether a function is increasing or decreasing, concave up, concave down in its end behavior, we need to look at what the function itself is actually doing. So we need to figure out which one of the 4 it goes in line with. Well, we have a positive a value, and our b value is between 0 and 1, so this is positive decay. And positive decay looks like this, essentially. So it starts really large and then is going towards the asymptote. So is it increasing or decreasing? Well, we can see when we draw what positive decay looks like, it is decreasing. Is it concave up, concave down? Well, it has like a half of a U shape that is going up, so we call that concave up. If you struggle with concavity, it is a very big idea in calculus, and you'll actually define it very well in calculus, so don't stress about that. End behavior, if we looked at the left, it is going towards positive infinity, and to the right, it is going towards the asymptote, which in this case is 0. The next one, we have a negative a value, so it's a negative a value, and our b value is larger than 1, so this is negative growth. So growth means going away from the asymptote, negative means it is going down, so we have a function that essentially looks like this. So is it increasing or decreasing? It is decreasing. But we can see it's decreasing in a different kind of way. This one is decreasing, and the amount it's decreasing is slowing down. and this one, the amount it's decreasing is speeding up. So different types of decreasing. And because of the slowing down, we have this concave up. And because of the speeding up, we have this concave down. Now, you can't just use this speeding up or speeding down to tell you which one it's going to be. You have to look at the graph and see what that graph looks like. As far as what's happening with the end behavior, we see on the left, it's on the asymptote, so that would be 0. And on the right, it is going further away from it in the negative direction, so that would be negative infinity. It's important to note that yes, the limit as x goes towards infinity is 0. Exponentials can never equal 0, at least without any transformations, and that is because when you repeatedly multiply or repeatedly divide, you're never going to get 0. You can get something really, really small, but you're never going to get to 0, because the only way to get to 0 multiplicatively is by multiplying by 0, which cannot happen with exponentials. So that is why we have this interesting behavior of it getting closer and closer to the x-axis, but not quite touching it. And last but not least, the last big idea is that vertically shifting exponentials adds a k onto the end, and that k is the horizontal asymptote. So if I wanted to shift the horizontal asymptote up or down, whatever I wanted it to be would be that k, and the equation of the horizontal asymptote would be y equals k. That is it for this lesson. If you have any questions, make sure you ask. Other than that, I'll see you in the next lesson.